All right, lecture B is going to go pretty fast here, and it's pretty high-level stuff. I already did put this on the folder on Google Drive that I shared with you, this thing here, so this PowerPoint. So if you can't quite catch up as far as taking notes, you should probably do so after class. So it's, again, pretty high-level stuff. It's going to be theoretical. It's kind of hard to take in real well in just a half an hour. Do your reading. Think about more examples on Wednesday, okay? Ideals. Ideals are a fundamental subject in the study of rings. What are they? They are special subrings. Just like normal subgroups are special subgroups, ideals in ring theory play the role that normal subgroups did in group theory. You might wonder, why do we call them normal subrings or something like that? I don't know. It's just traditional. I like the word ideal. What is an ideal? A subring A of a ring is called a two-sided ideal, though we will just say ideal. If for every R in capital R and for every A in capital A, both RA and AR, the product, which is, again, this is not necessarily a commutative ring, so these are not necessarily equal. But both of them are in A. Though I just mentioned they didn't have to necessarily be equal to each other. What does this mean? So, more sucking sounds. I practiced before class. I took a little swig of water here. Here we go. Is that good enough? It's still not perfect. Okay. More sucking sounds. Ideals suck things in. This set, RA, meaning consisting of all products like that, as little a varies over capital A, is a subset of capital A. In a sense, the R has been sucked in. There's a better sense of this in a minute here. Same with the other way around. AR, set of all products like this, is a subset of A as well. Like it sucks it in. Again, don't do that during the test. Okay, a proper ideal is an ideal of the ring that's a proper subset of the ring, and this is an important distinction to make, though. An important point of emphasis we will see here in a few slides. It's important to emphasize what a proper ideal is. It's technically not something we should really need to define so much, because it should be intuitively obvious based on what we've said about a proper subset. It doesn't equal the whole ring. The whole ring is an ideal of itself, but it's not a proper ideal of itself. What are ideals all about? They generalize properties of NZ in Z. That's the most basic example of an ideal. One of the most basic. If your ring is Z, the integers, NZ is the set of all integer multiples of n. They generalize the properties that has in Z, meaning in particular, as far as the definition goes, essentially what this is an ideal of Z, because if you multiply n by any other integer, whether it's a multiple of n or not, you get a multiple of n. Say that again. Mn is a multiple of n. It's in nz for any integer z in z, whether m is a multiple of n or not. Mn and nm are in nz. Okay? So it's noticing that property, that when you multiply a given integer, take n to be 7, by some other integer, doesn't matter what the other integer is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it doesn't matter, you get a multiple of 7. That's what we're generalizing. There is an ideal test though the ideal test is really not so much a theorem, it's really essentially the definition sort of re-emphasized in a slightly different way. A non-empty subset A of a ring is an ideal if these two implications hold. A comma B being in capital A implies that A minus B is in capital A. It's closed under subtraction, which was part of the subring test. Ideals do have to be subrings. And A and R imply that A times R and R times A are in capital R. I like to call this property superclosure. The subring test assumes both A and R are in A, and their product is in A. A is closed under multiplication. This is more than just closure of A under multiplication, it's superclosure. You got something in A, and something possibly not in A. R could be in A, but it doesn't have to be. Here's R, here's capital A, here's little a. Little r might be not in A. Doesn't matter. The product R times A and A times R is in A. Both of those are in A. Product gets sucked in, so to speak.
Is that
Question, Ike?
Is that a type 1 of bounding? This says AR and RA are both in R.
Yeah, that's an type. Thanks for coaching that. Thank you very much for catching, because I don't think I would have caught it without you catching. Okay? So that's what I was meaning with the picture here. Okay? So, talk about more examples on, well, I will briefly talk about some examples now, simple examples. Already mentioned this one. NZ is an ideal in Z. But really, to get your mind about what this is all about, to get your mind around what this is all about, takes more complicated examples. And that's where these other examples that I hinted at the beginning of lecture A come into play. You really want to study these. Pages 252, 253, 254, 255. Bunch of examples that are more complicated. Today we're only looking at simple examples. Here are some simple examples. For any ring R, the trivial subring is an ideal, and the non-proper subring R itself is also an ideal. I already mentioned NZ is an ideal of Z. Let A be an element of a commutative ring with unity. Then the following set is an ideal of R, the ring. It's got a name. It's called the principal ideal generated by A. That kind of sounds familiar. Generated by. This is analogous to the idea of a cyclic subgroup, but it's not the exact same concept in general. We do use the same notation for it, however, which does lead to confusion, this notation. This is not in general the same as the cyclic subgroup generated by A, which would be the set of all multiples of A, meaning n times A, where n is an integer, meaning A added to itself n times, 0 and negative A added to itself n times, where n can be any integer. This is the set of all products R times A as R varies over the ring. It's not the group operation. That's the ring multiplication. So it is a different concept. However, sometimes it does generate the same set. The cyclic subgroup generated by n is that as a subgroup of Z, but as an ideal, as a cyclic subgroup, as an ideal, it's the same thing as a ring ideal. So sometimes they can be the same set, but not in general. This is just illustrating, in this example, they happen to be the same. It's because the ring is Z, and therefore R would be in Z, that these happen to be the same for this example. But in general, they're not. And in fact, I'll show you an example down here. Okay, first the note, exactly what I said. If R is Z, and A is an integer in Z, this set is the same as the cyclic subgroup generated by A, but in general, this is a different concept. Consider this next example. Considering this ring, Rx, this is supposed to be the real numbers here, not the boldface. Polynomial ring, indeterminate x, coefficients are real. A is the set of all polynomial with constant term 0, meaning you don't have to write it. That turns out to be an ideal in here. Think about that quick. Subtract any two non-constant polynomials, or subtract any two polynomials with constant term 0. The constant term is going to stay 0. It's not going to magically appear to be non-zero. Multiply a polynomial such as x cubed plus 5x squared plus 4x with 0 constant term, so you don't have to write it, by any polynomial, constant term or not, you will get a polynomial with no constant term, 0 constant term. Constant term 0, different ways of saying it. Does that make sense? Can you imagine that out without me actually proving it? Writing out a proof? Even if this had a constant term, you multiply this polynomial by this one, you'll get a polynomial with no constant term of 0. Constant term is going to get multiplied by each of these things, and you're going to get a higher degree. It is an ideal, is what I'm trying to say. Furthermore, it is a principal ideal generated by x. You could write this. Every polynomial in this ideal can be thought of as some multiple of the polynomial x. By multiple, I mean ring element times x, where the arbitrary ring element is some other polynomial. Why? Because for any polynomial with constant term 0, you can factor out an x. That's why. But that's not the same as the cyclic subgroup generated by that polynomial. The cyclic subgroup generated by that, which I don't even want to write that way, would be the set of all integer multiples of x, meaning x plus itself an arbitrary number of times, 0, or negative x plus itself an arbitrary number of times. This would only contain these polynomials. That would be the cyclic subgroup generated by x if you're only considering the group operation of addition. Not the same as the ideal generated by x, but it's the same notation. But when we're talking rings, you should think of it as an ideal. does need to be emphasized that the ring does need to be commutative for this to be an ideal, a two-sided ideal, at least. There are one-sided ideals for that you can generalize this to, but we're talking about two-sided ideals. I said said ideals play the role that normal subgroups do in group theory. Why were normal subgroups important? Partially because you can create factor groups from them. You can do the same kind of thing with rings. You can create factor rings when you mod out by an ideal. In ring theory, ideals play the role that normal subgroups do in group theory. Let R be a ring and let A be a subring. This is really a theorem here. The collection of cosets, R mod A, look at the notation here. Set of all things that look like this, R plus A. These are cosets under the group operation, plus, and that is the way to write them in ring theory. This will be a ring under the expected operations, which will include a multiplication, if and only if A is an ideal of R. If A is a subring, definitely this will form a group under addition. You need the assumption that it's an ideal, not just a subring, to guarantee that it's a ring. That there's a multiplication that makes sense, that's well defined. What are the expected operations? There are these two things. This operation right here is the same as coset operation, coset addition with factor groups, written with additive notation. This coset plus this coset. How do you find the new coset? You add the representatives. These pluses really mean different things. This plus, for example, right there, S plus T, that's the group operation of the ring. We've got two ring elements. This plus right there, that's the new coset addition in the factor ring. There's a factor group here just initially. And the pluses next to the A's, these three are just, that's essentially just notation for cosets when the operation is addition. The new operation is this one. This coset times this coset. What do? You do the thing you'd guess you do, and you multiply the representatives and form this new coset. Quick example, quick simple example. We could consider, well, z mod nz for some n. Let's take n to be 4. What are the elements? The elements, it turns out there are going to be 4 of them. You could write them this way. Any other coset representatives would give you the same coset as one of these 4. What is the ring operation? It's essentially mod 4 arithmetic. You take 2 plus 4z times 3 plus 4z. You're going to multiply the coset representatives. Get 6 plus 4z. Which one of these things is 6 plus 4z? I hope you would guess that it would be 2 plus 4z. To confirm that, you could write 6 as 2 plus 4. And then this 4 can get sucked into the 4z. That's not really the sucking operation of an ideal in the definition of an ideal. That's a coset property from chapter 7. Okay. So this is essentially mod 4 arithmetic. This is isomorphic to Z4. Just as this happens in this ring, so does 2 times 3, which is 6, equal to mod 4 in Z4. It's going to be ring isomorphic to Z4. All right, final topic of the day. Prime ideals and maximal ideals. And definitely doing this in 10 minutes is not something you can completely get your mind around. But we'll do our best in 10 minutes. What is a prime ideal, first of all? A prime ideal A of a commutative ring R is a proper ideal, emphasis on the word proper there. That's why I set that out as a separate definition like the textbook did. It's a proper ideal of R such that the following property holds. A and B being in the ring, and A times B being in the ideal, implies either A is in the ideal or B is in the ideal. Say it again. A prime ideal, capital A, of a commutative ring R is a proper ideal. This property is going to hold if A were equal to R, but that doesn't mean R is a prime ideal in itself. Prime ideals have to be proper ideals. With this property, if the product of two ring elements is in the ideal, then one or the other ring element is in the ideal. Why would this be called a prime ideal? Well, as an example, if R is the integers, then the principal ideal generated by n is a prime ideal. If and only if, guess, n is prime, a prime number. That's why we call it a prime ideal. Why? Think about it. Well, let's just think of an example here. Consider the principal ideal generated by 5. If you've got the product of two things being in the principal ideal generated by 5, which will mean that it's A times B is a multiple of 5. 5 divides A times B. Then by Euclid's lemma, chapter 0, 5 must divide A or it must divide B. I didn't have to use a 5 here, I could have just used a P. Euclid's lemma. Which would mean A is in the principal ideal generated by 5, or B is in the principal ideal generated by 5. As an example. But I could have used a P, an arbitrary prime, instead of 5. Yeah, this concept generalizes the concept of an ideal generated by a prime number in Z. Think in terms of Euclid's lemma from chapter 0. All right. A little harder even to get your mind around is the idea of a maximal ideal. A maximal ideal of a commutative ring R is a proper ideal, once again proper ideal, of R such that whenever B is an ideal of R and typo here. A maximal ideal of a commutative ring R is a proper ideal, call it capital A, of R, such that whenever B is an ideal of R, and this is true, then one of these two things is true. Draw a picture for this. Got your ring R here. You got your ideal here A that is in the picture we're assuming is going to be a maximal ideal. If you've got some other ideal B, possibly other ideal B, between A and R, set inclusion-wise, it's got to either equal A or R, meaning you cannot have something like this. Something like this cannot occur. Cannot occur if A is maximal. B can't be set inclusion-wise strictly between A and R. It can't be an ideal that does not equal A and not equal R, but contains A and is an ideal no. B must be either equal to A or equal to R. A is maximal. It's worth noting that, once again, in the simplest kind of example, if R equals the integers, it turns out prime ideals and maximal ideals are the same. Same concept for the integers, not in general. Those ideals generated by prime numbers are not only prime ideals, they are also maximal ideals. This is a prime ideal. Here are its elements. As an ideal in Z, there's no proper ideal containing this ideal. What would it be? You might think, okay, maybe it's the ideal generated by 2 or 3 or 4. No. They're not going to contain that. Also, ideals generated by 6, 7, 8, 9, etc. are not going to contain that. Think about it. It's not a proof, really, because I'm only thinking about principal ideals when I think that way. But it is true. In the integers, these are the same concept. In general, they're not. 2 final theorems to look at. They're pretty fundamental. One is, let R be a commutative ring with unity and let A be an ideal of R. Then the factor ring, R mod A, is an integral domain if and only if A is prime, meaning prime ideal. A similar kind of theorem is the next one. Let R be a commutative ring with unity and let A be an ideal of R. Then the factor ring R mod A is a field if and only if A is maximal. So what's going on here? Well, what these theorems are going to do for us is they're going to give us essentially ways to construct integral domains and fields. The way we do that is we form factor rings by ideals that are either prime or maximal. Since these concepts are the same when R is the integers, these theorems are really the same when R is the integers. And remember, finite integral domains are fields. Now consider this, which does happen to be isomorphic to Zn. That's an integral domain if and only if n is prime. It's a field if and only if n is prime. I do have on the last slide the proof of the very first of these 2 theorems. It's actually not a very hard proof when you really understand the concepts well. But because the concepts are hard to get your mind around initially, it makes them seem difficult. I don't think I'll bother showing you that slide. It is on the slide. Well, I'll put it up here. But you can look at it in your book, and you can look at it in the folder that I shared with you on Google Drive. This proof is actually a fairly easy proof, even though it doesn't look so easy. Okay? It's proving the first of those 2 theorems. On Wednesday, We'll get into examples that are more complicated that illustrate these ideas. But you'll also be working on reading and doing some exercises that'll help get you more prepared for Wednesday as well. Really take those examples, those more complicated examples, seriously. We'll see you on Wednesday.